much for the introduction today. So as it says on the tin, today I'm going to be talking about exploration of highly correlated systems on quantum devices. Specifically, I'm going to first do a brief overview of quantum computing in general as the ADI group, and then pivot more towards my research on condensation phenomena on quantum devices. So let's first talk about the Mozziati group in general. So one really exciting avenue that's been explored in the Mozziati group is this contracted quantum eigensolver that Scott's developed. And this is an alternative to other eigensolvers on the quantum computer, and it's based on classical methods for solving for energies and reduced density matrices from the anti-Hermitian contracted Schrodinger equation. Scott has a contributed talk that's on the MeetAnyway platform under that contributed talk setting or heading. So I highly recommend you go check that out. He goes into a lot more detail than I'm going to go into. Another thing that Scott's been doing is looking into different error mitigation techniques. And one such mitigation technique is n-representability constraints in order to mitigate on the quantum computer. You guys have heard a couple different times already that near-term quantum devices are very noise prone, very error prone. So in order to apply any sort of methodology on these quantum computers to larger numbers of qubits, having more orbitals, that sort of thing, you need some error mitigation. And this representability constraint basically constrains the RDMs, the reduced density matrices, to represent n fermion wave functions. Sorry, my computer was not progressing. And Nick and Scott have benchmarked his Scott's quantum ACSC, the QACSC technique, using benzene isomers, and they found single millihartree errors, which capture a large part of the electron correlation energies of these isomers that have different levels of correlation. So again, highly plug his contributed talk. He goes into a lot of information on this. Another aspect that the group looks at is open quantum systems, and you've heard a lot about Kadei's work on the ensemble of Lindblad's trajectories. Here I highlight some more recent work that Anthony, a postdoc in our group, has done, where he has developed a general quantum algorithm to simulate non-unitary time evolution on a quantum computer by decomposing quantum operators into a linear combination of at most 4 unitary operators. And then last but not least in this very brief overview is Scott's work on using the quantum computer as an open system resource. He specifically looked at relaxations of stationary states at different frequencies on several quantum computers. And he found that each quantum computer acts as a non-Markovian bath with a unique noise profile. So that's just a brief teaser. I highly recommend looking at these papers. And let's pivot now to condensation phenomena, which is what I look into on the quantum devices. When I say condensation phenomena, I mean things related to traditional Bose-Einstein condensation, where bosons, which do not follow fermionic statistics, are able to aggregate into a single quantum state. They don't have to follow the Pauli exclusion principle. So when these bosons below a specific critical temperature condense into a single quantum state, that causes superfluidity of the constituent bosons. And the two types of condensation phenomena that I look into are fermion pair condensation and exciton condensation, where these are composed of fermions. So the fermions, of course, can't occupy or can't condense into a single quantum state, but these pairs of fermions, like electron-electron pairs forming a Cooper pair, become bosonic quasi-particles, and these bosonic quasi-particles can condense. So for example, Cooper pairs, electron-electron pairs can condense into a single two-particle quantum state, which we usually refer to as a geminal, below a certain critical temperature. And for electrons specifically, we're interested in this because the superfluidity of the electron-electron pairs, their ability to move without friction or dissipation has a lot of implications in electron transport and technologies, and but we haven't everyone in this area, the Holy Grail is looking for commercially viable superconductors with higher critical temperatures that aren't too energetically costly. So the other type of the quasi-particle that are the quasi-boson or the bosonic quasi-particles that I look into are Bose-Einstein condensates. And these, instead of particle-particles condensing into a single particle-particle quantum state, they're particle hole pairs that condense into a single quantum state. And why would we care about these exciton condensates? Well, because of the relative mass of the particle hole pairs compared to the particle-particle pairs, these exciton condensates should have higher critical temperatures, or should have the possibility of having higher critical temperatures. Additionally, that frictionless flow of excitons is particle holes that move without friction, which might lead to frictionless flow of energy. And one thing that the condensation and the superfluidity is known to lead to is something called counterflow superconductivity, where you have a bilayer system, which is fairly common in extended systems with exciton condensates. And the superfluidity of the particle hole pair causes there to be superconductivity in each layer, just in opposite directions on each layer. So as theorists, we're often interested in looking into signatures of condensation behavior so that we can say, hey, we have a condensate here according to our calculation. And so for traditional Bose-Einstein condensation, such a signature is a large eigenvalue of the one boson reduced density matrix. And that's because the eigenvalues of this density matrix correspond to occupations of one boson quantum states. So if you have more than one, an eigenvalue that's greater than one, you have more than one boson occupying a single quantum state. So more than one boson is condensed into a single quantum state, which is a signature of condensation behavior. Similarly, for these fermion pair condensations, we look at the two fermion reduced density matrix, where a large eigenvalue of this two fermion density matrix is the occupation of two fermion geminal. And so anything that's above one means that we have more than one pair of fermions occupying a single two fermion quantum state. And so we have fermion pair condensation. Very similarly, for exciton condensation, we look at the particle hole RDM, where a large eigenvalue of this particle hole RDM is a signature of condensation of, again, a value above one, although we do have to subtract out an extraneous ground state to ground state transition. Okay, so this is where I start talking about my work on exciton condensation of photon hole pairs on quantum computers. And this was really motivated by work in molecularly sized exciton condensates in the group at the time. Generally, exciton condensation, any sort of condensation phenomena, is looked into in like large systems, extended systems. But as Shiva, a former postdoc in our group, had previously shown, smaller scale systems could demonstrate exciton condensation, molecularly scaled systems, in fact. And the quantum devices at the time that I had access to were more similar to these molecularly scaled systems. Additionally, we saw these transmon qubits as being optimal representations of photon hole excitons, where these transmon qubits can be interpreted as anharmonic oscillators with photons as natural particles. And specifically, an individual qubit can either be in the 0 state or the 1 state. So you can think of it as a two orbital, representing two orbitals, each qubit representing two orbitals, and either the bottom state or the top state is occupied. So these two orbitals are particle hole paired. So if you have an extended network of qubits, or if you have multiple qubits, you have a two-layer system where you have, if it's n qubits, you have n degenerate layers in the bottom level and n degenerate layers in the top level, running to zeros and ones, and each state in the top level is particle hole paired to a state in the bottom level, which is very reminiscent of the Lipkin model, which is known to demonstrate condensation behavior in the large coupling limit. So we start with a 3-qubit preparation, and that's because the 3 qubits is the smallest number of qubits that can demonstrate the non-trivial entanglement. And we use this state preparation here in order to scan over different input parameters, which allow us to pair 3-qubit states that span all real 1-qubit occupation numbers, which means that we're spanning all possible 3-qubit correlation phenomena. So by scanning over those parameters, and this is for the QASM simulator results, we note that we see a large eigenvalue of the particle hole matrix, the modified particle hole matrix, for a wide variety of input parameters. So we do expect to have exciton condensation on the quantum computer. And we even get the maximal signature of condensation for a specific set of input parameters, which is n/2. So 3/2 is 1.5. But the question was, could we recreate this on a quantum device? And we found that we did indeed see exciton condensation on a quantum device for a wide variety of input parameters. And these results are before error mitigation. So it's not, we're actually seeing these condensates on the quantum computer. This is not an artifact of error mitigation techniques. So because for the 3 qubits, which are 3 particles and 6 orbitals, the Polytope was a very convenient framework to plot our entire scan. And if you notice, the eigenvalues go from 1 to 1.5, from like a purpley color to red. As you go from go towards the 0.5 corner, you get the largest signature, the maximal signature of condensate character. And that 0.5 corner is known to be the occupations of the GHZ state. Now, we weren't preparing the GHZ state in this initial scan. Only double excitations were allowed in this initial scan. However, the occupation numbers and the GHZ states could be expanded to higher numbers of qubits. The state preparation for that, for expanding the GHZ state to higher numbers of qubits, was known. So that's exactly what we did. We started with 3 to 5 qubits on IBM Yorktown. And then we went up to 15 qubits, which was the maximum number of qubits on Melbourne. And we went up to 53 qubits using IBM's Rochester. And as you can see, as we increase the number of qubits, we're increasing the signature of condensate behavior, but we're nowhere near what we expected our values to be without error. And, you know, as we're increasing size, we're increasing the number of C0 gates that we have, and we're on non-ideal like connectivities. So we are increasing error significantly for these quantum state preparations. And as you can see from this table, for simulated results, the GHZ state is expected to demonstrate the maximal condensate character of n/2. However, we're only getting up to about 4.74 on the 53 qubits, which should have a condensate character of 26.5. But we noticed something interesting, and that was, instead of having one large eigenvalue that demonstrated like that you have condensation character in one quantum state, we saw multiple islands of condensation. We saw multiple large eigenvalues. And if you look at the sum of all of these eigenvalues that demonstrate condensate character, we do approach this, or we do sort of seem to align ourselves with the maximal condensate character of n/2. Okay, so Now let's pivot to condensation of Cooper pairs on quantum devices. And specifically what I did in this work was entangle pairs of qubits into like Cooper-like bosonic pairs and formed superconducting-like states using extreme AGP wave functions. And that'll make a little bit more sense as I talk through what I did. One really important point here is now we have more of the traditional view of the qubits where 0 is unoccupied and 1 is occupied. Okay, so let's talk about an extreme geminal for a fermionic case. So we're creating an extreme geminal for the fermionic case. If we do a Jordan-Wigner transformation, and then select that J bar and J are consecutive. So if we pair consecutive electrons or qubits in this case, and then set the arbitrary get rid of a negative phase by setting the arbitrary theta value to pi, we notice that we can get a geminal that of Cooper pairs of electrons that it can be represented by 2 qubit excitations without approximation, because the difference between the fermionic and qubit statistics disappears using this Jordan-Wigner transformation. Similarly, we can prepare, or we can think about the BCS wave function, which is a linear combination of the number conserving AGP wave function, so it's non-number conserving itself. We can represent that using qubit operators without approximation, and we can think about that in terms of qubits now, the qubit representation as a tensor product of Bell states. Specifically, for those of you interested, the state preparation in the general case is shown in the top line, and then for the 4 qubit case, a schematic is shown below. Okay, so for our ensemble state, we did simulation using the CHASM simulator, and we used IBM's Melbourne to go up to 14 qubits because we were doing even state preparations, and Melbourne has 15 qubits. And we do this an increasing signature of long range order. That's lambda d value, so the large eigenvalue of the particle-particle RDM, where here we're looking at the qubits as particles. And that increasing signature of condensation is promising as we get to more and more extended systems. And we also do notice a large signature of condensation for Melbourne for experiment as well, although because of errors on the devices, it does take until we have 12 orbitals available. Okay, so the full BCS wave function, like I said, is non-number conserving. However, real world systems should be number conserving. And so we were able to project this full BCS wave function into the individual number conserving extreme AGP states. And if you notice, 2 of these number conserving states for any number of orbitals, the 0 and the R, where R is the number of orbitals, won't be entangled. So we should see larger eigenvalues for the substates that are entangled. And so this is the results for R equals 14 orbitals with different numbers of particles in the extreme AGP states, 2 to 14. And as expected with these extreme AGP states, we see a bell curve in the simulation results. We also see large signatures of long range order, off diagonal long range order. And one interesting facet here is that for the Melbourne results, of course, we get lower values, but that the bell curve that we expect is to have a right mode of skew, which means that the quantum computer is not treating particle and whole statistics equivalently, which does give us some insight into the error on the device. So in conclusion, our group utilizes quantum devices in a variety of applications involving a high degree of correlation. I specifically look into condensation phenomena. We created a highly entangled state, an exciton condensate of photon particles and holes, which can be used to model more traditional exciton condensations on 3 to 53 qubit systems. We also note in this case that unless sufficient effort is undertaken to prevent dispersion, that we see those multiple islands of condensation, the condensate character becomes scattered through multiple channels. And we note that the maximal entanglement of the GHZ state corresponds to particle-hole multipartite entanglement. We also prepare a superconducting-like state from Cooper pairing of qubits, which through a Jordan-Wigner transformation, as we described, are equally valid representations of condensations of Cooper pairs of fermions, bosons, and qubits. And we measure non-classical off-diagonal long-range order, which is a first step to simulating other systems with such non-classical long-range order on quantum computers. I would like to thank the Mazziotti group. This is an old photo, it's pre-pandemic, but at least it still has Cadet in it. So I wanted to specifically shout out Anthony, Cadet, Scott, and David, of course. And I'd like to thank IBM, the DOE, and the NSF. And does anybody have any questions?
Thank you so much, LeeAnn. That was a great talk. I have one question in the chat, privately sent, that is, for Cooper pairs, is the state in real space or case space?
For the superconducting work?
I believe so.
So the derivation actually doesn't specify what the pairing is. It's left in some unspecified orbitals, so it can be interpreted as being in either.
Awesome. Christian, do you have a question?
Yeah. Thank you very much for the nice presentation, LeeAnn. So I have actually a general question concerning this condensation phenomena, of those co-bosons. So actually, are you aware of any type of system or physical regime in which the density of those co-bosons is so high that the Pouli principle, which applies to the individual constituents, kind of affects the physics of such a system? Because just if you imagine the density was maximally high, then it's essentially the Pouli exclusion principle which prevents such a system from condensating. So you actually don't have then proper bosons anymore, but just hardcore bosons. And it seems to me that all the applications that I'm aware of, the density is so low that the hardcore bosons behave like proper bosons.
I'm not aware of any case where we have a high enough density. Like I was saying, we see that dispersion of the eigenvalues, or we see that dispersion causes the eigenvalues to scatter. So even though we should have gotten up to a like 26.5, like I was saying, in the 50 qubits, we don't see that. And whether that's down to error or down to what you were discussing, it is unclear. But I would say on these NISQ, the near-term devices, it's probably down to error.
Awesome. Do we have any other questions for LeeAnn? Either in the chat or if anyone wants to raise their hand. Oh, there's another one in the chat right now. What are U and V terms in the Cooper pair state?
What are what, Cadet?
The U and V terms in the Cooper pair state. Sanctual, if you wanna actually ask your questions too, you should feel free to unmute yourself and ask if you feel like it. Just or you can clarify. We'll see. It looks like Christian's got his hand up again, so we can potentially hear from Christian again while I wait for Sanctual to get back to me.
Can you explain again the story about this Polytope? So I didn't get fully the point. What did he exactly present? Are these like these n-qubit quantum margin constraints by Higuchi? Or is this just a ball and Dennis Polytope for 3 qubits?
Oh, the polytope that I presented.
Yeah. Somebody
So
stated n, so there was some quantum state on the left side with n qubits. So I was wondering what's
so
actually for Polytope.
The Polytope is related to the generalized Pauli exclusion principle. So the Pauli exclusion principle says that the entire Polytope can be occupied. However, with these generalized constraints, which are additional constraints because of on the occupations of the density matrix because of the anti-symmetry of the particles, we should only see occupation in the yellow portion. And Scott, one of his first works on the quantum.
I mean, of course, I'm fully aware of this. But,
oh, I mean, sorry, did I misunderstand?
Do you present there? I mean, it's like
the point
fermions in a 6-dimensional one-particle Hilbert space, or for 3 qubits, or for n qubits. Because it looks like a Polytope for 3 qubits, right? Not for n.
It's a Polytope for 3 qubits. Specifically, though, it's looking at 3 particles in 6 qubits because that's how we're interpreting the qubits here. And the point of looking at this was to kind of visualize the entanglement that we were getting and try to understand how to extrapolate to higher numbers of qubits.
And are all these points on the boundary of this qubit, or of this Polytope that you're showing here, or are they also in the interior? Because quite often they're like, in your case, it would be like spin symmetries, which directly pin the occupation numbers to the boundary. And then it looks kind of quite impressive when you move along the boundary, but at the end, you get just crossing of occupation numbers, and this explains this discontinuity on the boundary.
I'm not sure what the question was.
Okay, so not so important. I was just wondering, are all these points you're presenting on the boundary of these polytopes, or are they typically in the middle, somewhere in the interior of the polytope?
So all of these points are, we can reach the boundaries with different parameters that we put into our state preparation. But the number of calculations that we show here, the parameters that we input don't all completely get to the edge, but they do approach the edge. And if we had done more parameters, we probably would have gotten the edge. Because like I said, the preparation does span all occupation numbers for 3 qubits, or yeah.
Another point is, I mean, if you sample quantum states at random according to the Haar measure on the, let's say, 3 qubit level, it's actually quite difficult to reach points on the boundary because this probability to find points close to the boundary decays algebraically. And the decaying behavior is actually more or less the dimension of the full Hilbert space. So I'm quite impressed that you're so close to the boundary. But I guess you chose those points very carefully in such a way that you're anyway close to the boundary. Okay,
yeah, we chose the points pretty carefully.
Okay, so thank you.
Okay, awesome. And with that, I think that we are out of time. So thank you so much, LeeAnn. And oh, there's still another question there. I'm not sure how we want to run it, but I think that maybe if you want to send questions to LeeAnn privately afterwards, that might be a good way to do it. So I want to thank kind of all of our speakers, so Sabre, Pri, and LeeAnn for their awesome talks today. And we'll be reconvening again, I believe, in about 2 hours and 15 minutes for a panel discussion. So enjoy the day.